Good afternoon, ladies and gentlemen. My name is Hlaudi Masethe. I will be presenting my research work in progress. My topic is a Bayesian network approach to modeling word sense disambiguation task. This is just a portion of my doctorate program. This will be my presentation outline. I will give a background and motivation to the research, and I will speak about the context related to the NLP tool resource development in South Africa, and I will talk about the problem formulation, speak about the research objectives, and speak about the research methodology. Then I will move on to the proposed system architecture and the Bayes theorem. In terms of the background, I will first define some terminology that I use in my research. The first one is on natural language processing, which is basically considered to be an area of human-computer interaction, and again a field of artificial intelligence in computer science. It is basically devoted to making computers understand the spoken or written natural language. And the research is much more on word sense disambiguation task, which is a well known to be a critical module in natural language processing pipeline, which escalate accuracy of the extracted information. It is also known to be a method of allocating sense labels to the occurrence of an ambiguous word and computationally defining which sense of that ambiguous word is activated by its use in a specific contextual scenario. Agaya and Edmonds also define word sense disambiguation in natural language processing as the problem of defining which sense or a meaning of a word is activated by the use of the word in a particular context, a process which appears to be largely intuitive in people. Solving word ambiguity is critical for NLP as documents in a natural language such as Sesotho Sa Leboa, which is one of the 11 official languages in South Africa, contain many ambiguous terms where meanings can only be determined in a particular context. So this particular research addressed the problem of word sense disambiguation within the context of Sesotho Sa Leboa. Previously, it was known as Sepedi, and also it was known as Northern Sotho. It is spoken by about 4.7 million individuals in South Africa, and this particular language has a standardized written form of about 30 dialects, which some differ significantly from others. Sesotho Sa Leboa is also a highly polysymous language, having words that have multiple meanings. Polysemy remains a computationally challenging problem in contemporary computational linguistics. We have solutions that exist in the English language for word sense disambiguation. However, not much work has been done in this particular language, Sesotho Sa Leboa. WSD is also a solution to key developing human language technologies and also NLP applications for this particular language. speaking on the context of what exists, especially the NLP tools that exist in South Africa, English and other European languages had a lot of research work established and published already in WSD due to their simple morphological features. But in South Africa, for the last 2 decades, human language technologies development related to text and speech projects, which generated few NLP resources and applications that are treasured for future development of South African languages. These are obtainable from SADILA. However, access is also limited to these NLP resources. The Northwest University developed and implemented NLP web services for about 10 South African languages, and they are accessible via an application programming interface, and they are user-friendly web applications. In addition, language experts has annotated about 50,000 tokens per language for the researchers to develop core NLP technology pipelines. Those that have been developed so far is sentence separators, tokenizers, lemmatizers, morphological decomposition, part of speech taking, named entity recognition, phrase chunking, and language identification and optical character recognition. English is an Indo-European language which is different from Sesotho Sa Leboa, which is a Niger Bantu language. This particular language, Sesotho Sa Leboa, is an agglutinating with extensive and productive use of affixes, which tends to be different from English. So we have the structural difference between 2 languages. So far, we had an African WordNet project which has been able to show about 8,412 synset, only with 1,178 definitions that has been provided, which is about 14% definition of those synset. Now, meaning we don't have 86% definitions of those synset. Hence, we can say African WordNet resource has not been used for the development of HLT and natural language processing. A tool such as WSD has not been designed yet in South Africa. This is just to show the statistics of the African WordNet database for the different languages. So you can see that for Northern Sotho, these are the number of synsets, and we only have 14% of the definitions of those synset, with only 5,253 examples given under African WordNet database. So coming to the language structure, English is far different from Sesotho Sa Leboa. In Sesotho Sa Leboa, words in Sesotho Sa Leboa differ substantially from those found in European languages. And I will show an example later on. So we cannot easily adopt a word sense disambiguation tool that has been designed for European languages due to some of the challenges that we find in Sesotho Sa Leboa on the language structure. These are some of the challenges that we find different from European languages. For example, we have disjunctive and conjunctive writing styles in Sesotho Sa Leboa, and this poses a computational problem to identify the target word. I'll give an example later on. Language resources such as WordNote is not fully developed, as I indicated that 14% of the synset has been defined, and 86% of the scene set has not been defined yet. So complexity of rich morphology of Sesotho Sa Leboa also poses a linguistic issue, which makes it difficult to solve the word sense disambiguation problem. Again, Sesotho Sa Leboa is a language rich in metaphor. And this...
Hi Dan, so sorry to interrupt you.
Okay. Sesotho Sa Leboa is considered an agglutinative language, which makes it computationally difficult to develop natural language processing pipelines. Desai and Browning observe that to solve the problem of WSD, we need to have an understanding of the types of ambiguities in a language that is required. So Chokwe also further distinguished the language using 3 different types of ambiguities, which also pose a challenge for computational linguistics. The first ambiguity type is orthographic ambiguity, where we have a problem with word divisions. Like I said, in Sesotho Sa Leboa, we can do conjunctivism, and it's also a disjunctivism. So we can do both writing at the same time. And a word that is written conjunctively will have a different meaning with a word that is written disjunctively, although they may look alike. This is one of the example. This word is written conjunctively and it loses a meaning. But this one is written disjunctively and it will also have a different meaning. So the same word written conjunctively will have a different meaning with the same word written disjunctively. Another type of ambiguity is lexical ambiguity, where we have polysemy and we have homonymy. Now polysemy is the same word but may have 2 or more different meanings. And this has to convey related meaning inclusively. Like the word lilimi will have a different meaning depending on the context that it is used. And 2 or more words may be identical, may be pronounced the same, may be written the same, but they may convey unrelated meaning. An example is the word lewa. It may have different meaning also. Again, the language has a foreign influence. Like we tend to use words from Afrikaans and we have adopted those words in our language. And depending on how the word is used on a sentence, it will give a different meaning. Here is an example. This sentence, Mushimanu yo unyaka nteipa. The word nteipa is actually an adopted word, is used because of the foreign influence, but originally we don't have this word in our language. But since the word is already being used, one sentence can have 3 different meanings. It can mean rape, it can mean recording, it can also mean measuring on the same sentence. So it will depend on the context. We also have the third type of ambiguity, which is structural ambiguity. With this one, is an ambiguity due to the different structures which are permitted by rules of syntax. So, for example, this sentence will have a different meaning. So, the syntax or the grammatical structure may give a different meaning if it is written in this particular format. Now, the second sentence basically means the police have arrested the boy who stole at the bank yesterday. But it is not clear on the sentence whether the police have arrested the boy who stole. What is not clear about the remaining part is whether the boy who stole was arrested yesterday or was arrested at the bank, or the boy stole at the bank or the boy stole yesterday. So the whole sentence needs to be paraphrased to have one meaning. So lexical ambiguity in Sesotho Sa Leboa cause computational semantic problem in natural language processing to identify the lexicon of a language. The main problem in the study of word sense disambiguation is linking context and senses to an ambiguous word. This is another example of an input sentence in Sesotho Sa Leboa which Google cannot be able to translate correctly. For example, this one, Mosadi Unuka Seshebo Kaletswai, the correct translation of this sentence into English is a woman is seasoning the food with salt. However, Google Translate translated differently because the word nuka is an ambiguous word. So from the above given example, it is noticed that the word nuka creates ambiguity by representing different senses at different contexts. Again, I can give another example of a polysemy sentence. When we say batuba, this may denote at least 5 senses based on lexical ambiguity. Like the verb stem has numerous distinctions of meaning. Like it can mean people practice witchcraft. It can mean people are well health-wise. The same sentence can mean people wake up early in the morning, people are waking up, or people become wise, or people become rich. So it will have to be based on the context for one to interpret or translate this particular sentence into English correctly. Suppose that we have data point W for ambiguity with W1, W2, and Wn of n features given as a set of target weight of ambiguous weight in Sesotho Sa Leboa. So we intend to find an accurate sense to the ambiguous weight, solving the n features with these particular senses. So we can state that Bayes' theorem is stated as the probability to find the sense given an ambiguous weight. So that's basically what we are trying to find in this particular research. The objective of the research is to model the posterior conditional probability distribution of the outcome variable, observing the new evidence of the lexical ambiguity of the weight. In this research, we construct a Bayesian network manually with acquaintance of the fundamental sphere. Hence, we compute the probability of word sense disambiguation when polysemy and homonymy words are observed in lexical ambiguity. So basically, we intend to construct a Bayesian network for word sense disambiguation, then use variable elimination algorithm to compute marginal probabilities efficiently. So we have adopted a Bayesian network, and it's known as a belief network or causal network as a methodology, and is defined as a graphical model that represents multivariate probability distribution represented in a directed acyclic graph. So Bayesian network is basically a tool to model and reason with uncertain beliefs and consists of qualitative component named in a directed acyclic graph and quantitative component in the form of conditional probability tables to quantify the dependencies between variables and their parents in the directed acyclic graph. So the definition of conditional probability is fundamental to the subject of word sense disambiguation, and from the derivation of the Bayes' theorem to research, we can obtain the posterior distribution of the model parameters or even perhaps a mathematical formula that can help us to predict density of the future observation. So this is basically the notation that I will be using. W for ambiguous weight, and the letter S for senses of the ambiguous weight in W, and this will be for the context of the ambiguous weight, and P, it will be for the probability, where we try to find a candidate sense for the ambiguous weight. So we can derive a Bayes theorem mathematically to obtain the predictive density. So this is basically just to show how we derive our Bayes theorem based on our notation that we have utilized. So this is just the mathematical formula that we show how we can derive our Bayes theorem. These are some of the formulas that I will refer to later on in my presentation. So basically we adopted a Bayesian classifier to solve word sense disambiguation problem. So this is a process to determine the correct accurate sense, and it is given by this particular formula which we derived from our Bayes theorem. This is just a proposed Bayesian network where we have a polysemy word or a homonymy that give a lexical ambiguity, and we can solve that using a context. And once we can find the context of that particular ambiguous word, then we can be able to allocate a sense to that particular polysemous or homogeneous homonymy word. And we also use equation 1, which was indicated earlier on, so that we can in principle calculate the joint probability of binary states in hierarchical statistical model. Here we just outline the joint distribution which represent the given Bayesian network in this particular diagram here, figure 1. So this is just how we outline the joint distribution to represent this particular given Bayesian network. And again, we can use this particular formula for eliminating variables. So this is just an algorithm that we use to eliminate algorithm for inference on our network given in figure 1, our Bayesian network. So the variable elimination algorithm is formally defined as a loop over the variables as ordered and eliminated in that ordering. In this particular presentation, I didn't give a formula for the algorithm in full for variable elimination algorithm, but those that are acquainted with the variable elimination algorithm, they know that we define it as a loop over the variables as ordered based on our Bayesian network, and we can eliminate certain variables in that particular order. It is a modest and universal exact inference algorithm used in probabilistic graphical models such as Bayesian network. So based on our Bayesian network, we have derived a computation to calculate the marginal probability from our variable elimination network. And we also used RStudio, specifically the BNLen package, to implementing this particular formula for variable elimination to compute our marginal probability. This is basically our conditional probability table for our Bayesian network. And we start eliminating the first two variables on our Bayesian network using this formula. Then we move on and eliminate the third variable on our Bayesian network, and continue like that until we are able to eliminate all the other variables. The idea is to calculate the probability to check if we can be able to assign a particular sense to the word that is ambiguous in our sentence. So prior marginal computation for the variable sense gives us a probability of 58% to disambiguate and ambiguous homonymy and polysemy word. So basically, based on our formula, we are saying the variable that will have, or the sense that will have a higher probability, will be the sense that will be allocated to that particular lexical ambiguous word. So in a network structure, the first step, we construct a Bayesian network to determine the structure which defines each node's dependency relationship with the rest of the network. In our model, we are making these independent assumptions on the structural relationship between words. And specifically, given the sentence S and its past tree, which we'll talk about, we can automatically construct a graph, and we apply context-free grammar, which is basically a popular model used when it comes to developing a parser. This is our proposed system architecture. First, we input sentences that may contain an ambiguous word. Then we do pre-processing. In other words, we do data cleaning. We remove inconsistencies by applying the NLP pipelines such as tokenization, part of speech taking, lemmatization, and named entity recognition. By doing this, we are basically constructing a parser tree. And once we have the parser tree, we can identify, using ambiguity checker, an ambiguous word on our sentence. Then we can use a Bayesian network based on the context that I indicated earlier on to output the accurate sense of the sentence. So with a Bayesian network, basically we are saying the sense that will have a higher probability will be the one that will be allocated as an accurate sense for that particular ambiguous word. So the proposed system architecture, as shown in the previous slide, shows pre-processing modules and ambiguity checker, which continues to check occurrence of existing ambiguous word from the input sentences using ambiguous corpus. This is just an example of part of speech taking for the sentence that has been indicated here. And based on this part of speech taking, we can now construct a parser tree. And that parser tree will now serve as our Bayesian network, and we can now calculate the probabilities to allocate an accurate sense to a particular word that is ambiguous. So you can see that the second sentence will have a different part of speech taking. Even I have three sentences that I've indicated here as an example. They all have different part of speech taking. which will also develop into a parser tree, which will always be different. And the parser tree automatically can become our Bayesian network, and we can now calculate the probabilities on that Bayesian network to allocate the accurate sense to an ambiguous word. So just to narrate a bit about parsing network, the Bayesian network describe parsing tree which can be built automatically for any context-free grammar. Obviously, the context-free grammar in Sesotho Sa Leboa will be different from a context-free grammar in English and other European languages. So the grammar must be written in a way that synthesizes the structural information of relevance to the disambiguation process. This is not a requirement of the methodology for building the parsing network, but rather of the mechanism where the syntactic and semantic networks are interconnected. Bayesian belief networks are models. For example, we are estimating the probabilities of multiple possible interpretations of an ambiguous utterance. The network will allow us to compute the posterior probability of each interpretation as each piece of evidence arrives. In addition, the use of Bayesian network as a probabilistic estimator can allow us to incorporate any kind of evidence, syntactic and semantic, which will allow us to capture the syntactic probabilities captured by graphical models like the CFGs, which I indicated earlier on, while augmenting them with other probabilities. Thank you. That will be the end of my presentation, and I also want to thank you for giving me the opportunity to present and discuss my research in progress on a Bayesian network for word sense disambiguation task for Sesotho Sa Leboa. Thank you.